All right, the next section is 4.7. We're going to skip completely. We're not going to talk about it. It's about radical reactions in polymers. We don't really have time to really spend on those two topics. If you would like to read them, if you want to know more about them, that's fine, but you're not responsible for them. Sections 4.8, 4.9, and 4.10 are on a concept called resonance. It's an extremely important concept. And it's so important that I want to actually do an in-class lecture on this. I don't want to do notes like this because I want to stop, I want to ask questions at every little step. I want to do lots of in-class problems. So we're going to spend a little bit of time in class on the section. What I do highly recommend you do is go and find YouTube videos on resonance. Just type in resonance organic chemistry. Watch the video so you kind of have an idea of what it's about. You should read the book about resonance, but it's very important, and we're going to be using it quite a bit. And like I said, I want to do an in-class. Also, Khan Academy. Khan Academy, some of you might know about it. If you go on Khan Academy, they have some videos. They're kind of intro type videos, which is good because it gives you an idea, but I'm going to go more into it. All right, so for these three, so 4.8, 4.9, 4.10, we're going to do more in class, that lecture, and or you can watch videos beforehand. All right, the next, the last part of this chapter, now it's all about alkynes. We've talked about all these reactions with alkenes. Now let's do the same reactions with alkynes, and let me tell you, this is going to be kind of quick because whatever you can do with alkenes, you can do them twice with alkynes because you've got a triple bond. So basically what you've already learned, we're going to just show you again, but with a triple bond. But before we do that, there was some extra naming rules that I do want to show you. The first thing that we've already learned is that when you have a triple bond, you start counting from the side closest to the triple bond. So let's look like a chlorine there, CH3. All right, so you have a triple bond, they end in "-ine", I-N-E, and you start counting from the side closest to the triple bond. You still look for your longest continuous chain. Here's my substituent. So this would be called 6-chloro-hept-2-ine. Okay, so that we've already learned. There's one new concept I want to talk about, and that's what's called enines. Enines. All right, what is an enine? I think you can probably figure out what an enine is. It is a compound that has a double and triple bond. Okay, that's an enine. Now, there are three possible things you can do with an enine, okay, as far as naming them. Okay, so your triple bond, so whichever bond, your double or your triple, is closest to one of the ends, that gets the priority. So let me show you, instead of writing it down and saying all this crazy stuff, let me just show you an example. It's the best thing to do. All right, so what happens if you, so the point is I have a double bond and triple bond. The rule is you start at the end closest to the double bond in the double bond case, start at the end closest to the triple bond case. What happens if you have both? Well, you start at the end closest to whichever pi bond is closer to a side. Doesn't matter if it's triple or double. Notice the triple here is starting at carbon 1 and carbon 2. The double bond, it's closest to the right side. So that'd be 1, 2, 3. So my double bond starts on carbon 3, my triple bond starts on carbon 1, so in this case the triple bond will get the priority. Right? If it was the other way around, if the double bond was at this end, and you had CH2, C, triple bond, CH2, CH3, this time your double bond gets priority. So in this case, alkyne gets priority. In this case, your alkene gets the priority. Okay? So this is numbered 1, 2, 3, 4, 5, 6, 7. Okay? So at the top case, 1, 2, 3, 4, 5, 6, 7. So the name of this, I'm going to have to put it down here, is going to be hept. All right, now it's an enine. You have to name it alphabetically. So it's hept, 4-ene, 1-ine. Okay? That's how you name it. That would be this one up here. The one below would be called hept, 1-ene, 4-ine. That would be this one. Okay, so these are enines. you name them ENE, YNE, even though they're an enine, which is EN, YNE. Okay? What happens if they are equal, if they are equidistant to the side? So you have a triple bond, CH2, CH2, CH double bond, CH2. Notice in this case, if I start on the left side, it's 1, 2, 3, 4, 5, 6. So my triple bond starts at carbon 1. If I start counting the other way, 1, 2, 3, 4, 5, 6, my double bond starts at carbon 1. They are tied. What do you do in this case? Well, since ene alphabetically is before yne, the ene gets priority. The alkene gets the priority. Alkene gets priority. So technically your alkene gets the priority unless your triple bond is closer to one of the ends. Okay? So this would be this is the way we're going to number, like that, not this top way. All right. So this would be called hex 1 ene 5 yne. Okay. So that is the rule with naming. Now let's get to the reactions. And like I said, most of these reactions are the same. There's one reaction at the end, which is very important. I'm actually going to make it into a different reaction file, or lecture file. The rest of them I'm going to kind of go over quickly because they aren't anything spectacular. Not many mechanisms. So what happens if we take a triple bond and add it with hydrogen? Now hydrogen is always in excess. That means you always have a lot more hydrogen than you do of your triple bond. Well, what happens is it completely hydrogenates your triple bond. You do not stop at the double bond. Okay, so no stopping at alkene. All right, your hydrogen just keeps adding until you completely hydrogenate it. All right. However, there was a scientist who discovered a catalyst. It's what's called a poison catalyst that actually does stop it at the double bond. All right. So this is a special reaction for triple bonds, and it's what's called Lindlar's catalyst. That's the name of the scientist, Lindlar. Lindlar's catalyst. It doesn't matter what the catalyst is. We're not going to go over what the catalyst is. If you really want to know, look in the book. But it's what's called a poison catalyst. It deactivates your catalyst a little bit so that it just reacts with the pi bond on your triple bond, but not the pi bond on the double bond. So Lindlar's catalyst plus hydrogen stops at the double bond, and it always gives you the cis compound. All right. There is a way to make the trans, but it's just too much information for this class. We're not going to talk about the trans. All right. So Lindlar's catalyst stops at the double bond, just completely hydrogenate it with our platinum oxide or the palladium on carbon. We learned that last a few sections ago. That will work too. Okay. So that's hydrogenation. All right. What about HBr? Let's take a triple bond. I'm going to take a terminal triple bond. Terminal means that you have a hydrogen on one side. It means that your triple bond is at the end of the chain. So it's terminal, it's at the end. If you have one equivalent of HBr, it does exactly what we've seen. The bromine goes to the more substituted carbon, and the hydrogen goes to the least substituted. So you form a double bond with a bromine on it. All right? If you add two equivalents of HBr, let's do the same reaction, but add twice the amount of HBr. The way you show that is 2EQ, meaning equivalence. Equivalence means, like, let's say I'm adding 1 mole of my triple bond. I'm going to add 2 moles of HBr, twice the amount. What you get is you get 2 bromines added on, and you get rid of your double bond. And that's because it does the reaction twice. The mechanism is identical to the mechanism of the alkene. I'm not going to go over it again because we've already gone over it. Okay? So that's what happens in this case. Now let's look at the reaction if you have X2. It doesn't matter what X2 is. It could be Br, chlorine, or iodine. Remember, not fluorine. X2, remember X is the anti-addition, so you get the trans product. So that's what you get with one equivalent. Why don't you put this on pause and write what would happen if you add 2 equivalents of X2. Put it on pause and write the product. Alright, I have the product for you. Notice you get 4 X's. It happens twice. So the first equivalent makes this compound up here, and then you have a second equivalent there. It reacts with that, just like the mechanism we saw in the previous section, to give you 4 halogens on your compound. Okay? Next one is hydration. What happens if you hydrate it? All right, this hydration has special ingredients. It has a mercury compound. So it's actually mercury. It's a mercury 2 ion. I believe your book uses mercury sulfate, MHgSO4, and acid, H2SO4. Those are the ingredients. Those are the reactants. We're not cooking here. They're not ingredients, they're reactants. You add mercury sulfate and sulfuric acid, and what you form is you get the OH on the carbon, so it does the same type of thing as we've seen. The oxygen goes on the more substituted carbon, all right? And you form one of the pi bonds, and you form this double bond to a CH2. Well, this compound is actually kind of unstable. It's what's called an enol. All right, enols don't exist. What they do is your pi bond switches places with your hydrogen on your oxygen. So instead of having the pi bond on the carbon-carbon bond, you have a pi bond on the carbon-oxygen, and this extra hydrogen goes on your CH2 to give you a CH3. So notice you form a ketone. So you do not stop at this. Do not stop at this product. It actually forms this compound. Okay, this is just a quick intermediate. It forms that, but then that intermediate is not very stable. It reforms. All right, it's actually a rearrangement, some sort of rearrangement. We've talked about what rearrangements are to form this ketone. All right, and that is the hydration reaction. I'm going to stop at this point, and I'm going to do another section, which is the very last reaction, which is the acetylide formation and the reaction with the acetylides.